everyone. Dobro jutro to our Serbian colleagues. We're very sorry for this short delay, some technical problems from our side. Welcome to the workshop heat pumps with natural refrigerants and multiple renewable sources for the decarbonization of multi-family buildings. The workshop is organized as part of the 3HP EU-funded project. My name is Spyridon Pantelis. I'm the secretary of REHVA's Technology and Research Committee, and I will be the host of today's workshop. For those that are not familiar with REHVA, REHVA is a federation of European heating, ventilation, and air conditioning associations, founded in 1963, and represents over 120,000 HVAC designers, building service engineers, technicians, and experts across 26 European countries, including Serbia, of course. We're very happy to participate to the 52nd KGH International HVAC Congress, and I would like to thank a lot Marija Todorovic and SMEITS for their kind invitation and the organization of 52nd KGH. I hope you will enjoy this workshop. Before we start, I would like to remind a couple of housekeeping rules. So the workshop is recorded. The slides will be sent to the participants, and all attendees are muted by default. At the end of the workshop, we will have a session with open discussion, where you can use the raise your hand function that you can find, as you can see, on the bottom of your panel. And you can ask the floor to discuss in case you have any questions with the speakers. So the agenda of today is first, Danny Carbonell, project manager from SPF, will introduce the 3HP project. Then Rafael Gerber from HEIM will talk about heat pumps with natural refrigerants. Then Xavier Peña from Tecnalia will talk about experimental results of the dual source heat pump system. And then Thomas Friedrich from IZVORE will talk about the social acceptance of 3HP systems. I would like at this time to introduce shortly our speakers. So Danny Carbonell is a 3HP project coordinator, team leader on thermal systems and modeling at Institute of Solar Technologies at SPF. At Eastern Switzerland University of Applied Sciences, is a thermomechanical engineer with more than 13 years of experience in the field of simulation of heat and mass transfer phenomena. He is currently coordinating several national funded Solarize-related projects, such as ICEX, SolariUp, Big Eyes, and has participated in many other projects. He has 7 years of experience in systems simulation, in Transys and Polysun, in the field of solar thermal and heat pump systems, with a strong focus on solarized systems with 14 publications on this specific topic. I'm pretty sure this number is much higher at this point. Then Rafael Gerber is a development officer from HEIM in Switzerland, offering sustainable heating systems with wood or heat pumps. Rafael holds a degree in mechanical engineering and has developed refrigeration and heat pump systems for 15 years. He's working for different companies. He has led different projects to implement groundbreaking technologies, such as indoor installation using flammable refrigerants or performance enhancement using CO2 as a refrigerant. I'm sorry. Then Xavier Peña Anton is a senior researcher in the area of thermal energy at Tecnalia R&D. He has a degree in mechanical engineering and master in fluid thermodynamic engineering and in innovation technology management, and he's a PhD student at University of Basque Country. He has more than 15 years experience in research and development, both in private companies and in technological centers. His career has been focused on the development of innovative thermal equipment and components with natural refrigerants, from the design and modeling using simulation tools to experimental testing and validation. Thomas Friedrich is a social scientist at the Institute of Social and Ecological Research in Frankfurt, in Germany. He's a PhD in social and cultural anthropology, and he has extensive multidisciplinary research experience and is particularly interested in transformation process towards a more sustainable society. Together with his colleagues, he also collaborates with non-scientists and practitioners in many projects to both generate enhanced transformation knowledge and to bring this knowledge into practice. As a social scientist, he specialized in qualitative empirical research. I will go straight to the first presentation from Dani Carbonell. And please, Dani, if you could share your screen. Thank you very much.
Do you hear me now?
Yes, we can hear you.
Okay. So good morning, everyone. Yeah, so as Spiridon said, I'm the project coordinator. I will not say too many things now because otherwise we are running out of time. I had some slides to present our institute, but I think it's better to just present the topic and discuss later on. The slides will be there in case you would like to check what are our usual topics where we work with. So let's focus on the 3HP itself. It's an H2020 project. We started to work in 2019 and it will last until 2023. It's a project where we are aiming to push the technology readiness level from 3 to 5 in a project size of around 5 million. Here you have the logos of the participant consortium. And this is, of course, a new research and innovation project where our aim is to develop systems that can provide heating, cooling, and electricity to multifamily residential buildings. And we want to do this by using electrically driven natural refrigerant heat pumps that we are coupling with photovoltaics. Our main target is to achieve 80% renewable on-site share with a net zero energy concept, which basically means we are producing all electricity we need and we exchange 20% with the grid. We are developing systems that are aiming to reduce installation costs by 10 to 15% compared to current heat pump technologies that achieve the same efficiency. And this will also lead to reductions of emissions to about 75%. In the project, we are aiming to develop two system concepts. One is what is called a solar dual sourcing system. Basically, it's a heat pump base system with a heat pump that can be reverted, so it can provide heating and cooling. And this heat pump can use boreholes or an air as heat sources and heat sinks. And the innovation is in the heat exchanger that we will explain a little bit later on, that can use these two sources simultaneously. This is a system that it's meant to be used for South Europe or for mild heating dominated things, but it has a great benefit if it can be used for cooling as well. The second system is what is called a solar ice slurry system. This is a system used for heating dominated climates where cooling is just an add-on feature, but it cannot deliver too much of it. In this case, we have also a heat pump as a center of the system, but instead of using ground or air as heat sources, it uses solar thermal collectors. And because solar thermal cannot always provide heat at night or cloudy weeks, then we need an additional heat source. And what we use is a water storage that will ice in winter. So this storage will be 3 months in winter in ice form, and otherwise it will be on water state. And this is a substitute of a ground source heat pump where we don't have to tackle regulations, and also we don't need to drill boreholes and things like this. So in terms of the ice, what exists today, it's what is called as ice on coil. This you can see a typical ice storage. This is on construction. So at the end, all this volume will be packed of tubes, and then ice grows on the external part of these tubes. This is a very mature technology. It's relatively simple, no moving parts. But these heat exchangers in this volume add significantly to the cost, and this ice layer reduces the heat transfer rate and then the efficiency. Because you need tubing everywhere, the cost scales by kilowatt and not by kilowatt hour and not by kilowatt. On the other hand, we can have ice slurry concepts with scrape surface heat exchangers. This is something that exists commercially in Europe, where we have a cold surface where ice is built, and then there is a rotating machine that scrapes ice from this surface in a continuous manner. But this mechanical device adds complexity, investment, and operational maintenance costs, and that's why it's not very widespread in Europe. And despite the fact that this concept scales by kilowatt, which is good, the scalability, it's limited to these mechanical devices. So what do we propose instead? We propose is a nice slurry system. We like the concept of ice slurry, and I'll tell you why. I mean, ice slurry is considered to be a mixture of ice particles and suspension in liquid water, and the ice storages with these are free of heat exchangers, and then the heat transfer surface is always free of ice, which means that it's very efficient and independent on the quantity of ice we have in the storage, because we are decoupling ice generation and ice storage, which means that our cost scales by kilowatt and not by kilowatt hour, and that's why we can reduce the cost of the storage by 50 to 80%, which then ends to a cost reduction on the system level up to 10%. And our concept to use the ice slurry instead of the scraper is what is called a supercooling method. So basically we take water, we cool it below the melting point of water, we cool it further down in liquid state until we trigger nucleation in an ice crystallizer. We do this in a controlled manner, and then we release the latent heat of water. The difference between the melting and the actual crystallization point of view is what we call a supercooling degree, and the higher the supercooling degree, the higher the probability of freezing. So what we have developed already are heat exchangers, relevant heat exchangers using in standard heat pumps that are using isophobic coatings on it, coatings that repel the formation of ice or delay it. And we have compared this with untreated heat exchangers. Here we have the results of this water outlet, which means kind of the supercooling degree, from a reference untreated surface and different isophobic coatings developed by our partners. And we could see that we could improve the supercooling degree by a factor of 44%. And we are able to reach on this testing, we were able to reach powers in the range of 5 kilowatt. Now these heat exchangers are applied into heat pumps, as I will show later. Another development on heat exchanger for the heat pumps is what is called a tripartite gas cooler. This is a heat exchanger used for a CO2 heat pump. And the benefit of this is it can provide simultaneous heating and cooling, heating and domestic hot water very efficiently. And the reason is because with these heat exchangers, we can follow very good what the CO2 is doing in the gas cooler, which makes the system or the heat exchanger very efficient, very compact. And this is an evolution of what it was tested before an NTNU. This was the old design, helical counterflow tube-in-tube heat exchanger, which had a weight of 34 kilos. Now we are reducing it to 5. This heat exchanger had a tube length of 32 meters, and now we are only using areas of 1.7 square meters. So the actual unit is a combination of 3 of these small heat exchangers, which ends with a very compact unit. Another development from the project is to go to heat pumps. So we are using all the heat exchangers that we have developed on a device, and we are coupling this to heat pumps. One development is a CO2 heat pump. That's a power control floated evaporation with ejected technology, where it's using this tripartite gas cooler and the supercooler that we showed before as an evaporator. And this is meant to be used for residential buildings with high shares of domestic hot water. And this is using the solarized lorry concept with cooling as an additional. Here are some results, but they will be shown later. I will just highlight that with this heat pump, we can reach 70 degrees on domestic hot water while producing a space heating at the same time with efficiencies in the range of 4 when the evaporation is the limit in the evaporation is at 5 degrees. So it can reach very high temperatures at a very high efficiency. Another major development of the project is what is this dual source sink heat pump, which is based on the very innovative dual sourcing heat exchanger. So the main innovation of this development is that it can not only use brine and air as heat sources, but they are being used directly. It's not, they don't need an indirect cycle in between. So the heat exchanger made custom for this application has been developed. And this has been applied into this heat pump that is now being tested. That was tested on a first campaign, and now it's tested. It's being tested on a second campaign. This again is a system that is meant to be used for heating and cooling, and for mild to warm climates. Another development of the project is to do advanced controls, and we have 2 levels of controls. One is a efficiency drift self-diagnosis system, which is basically a control that we implement into a heat pump in order to detect automatically degradation or faults. So the idea is that we have a control that learns for a period, and when it learns the operation of the heat pump, then it can enter into a monitoring status, where here we can see an example. This is the COP of a heat pump where it has been forced to have an error of falling. And we can see that the COP is decreasing, and then the algorithm automatically detects when there is a drift of this COP and sends warnings. And the idea is that then maintenance will be simplified, and you can get an advice when your system is not operating where it should be. Another thing that goes above this control is what is called an advanced energy management system, a control that controls the complete system in itself. It's based on model predictive control with an optimization algorithm on top that does 24 hours forecasts for everything, weather, occupancy, demands, and then it does a dispatch of all the devices, and it tells each device when it should operate doing this forecast of 24 hours. And the idea and the goal of this is that we are aiming at reducing the energy cost by 50% compared to a rule-based control, and increasing a renewable share of 80%. All the developments from heat exchangers, they go to heat pumps, and then the heat pumps, they go to a complete system. And all the system is tested in what we call a hardware in the loop dynamic system test. This is a concise cycle of 6 days that are representing the whole year. This kind of testing brings the technology at least to TRL 5. And here we have an example where the gray part is what we emulate and simulate, and the blue part is what we installed in the lab. So basically everything we develop is here, and everything that we don't develop and we don't need to have physically, then it's emulated and simulated, like thermal collectors, photovoltaics, and so on. The demands are not, of course, there, but all for example, in the case of ice storage, it will be the ice storage, the heat pump, the storage, the advanced energy management system. So we will also test a rule-based and advanced energy management system, battery and inverter. All this is installed in our lab. And last but not least, we have a part on technology acceptance. The main goal is to understand and improve the stakeholder acceptance, and analyze and identify the interests of the key stakeholders that have a role in implementation of the systems we are developing. The methods are qualitative interviews and regional stakeholder workshops, and you will get to know more about this in a later presentation. So this was our team, or it's our team. This is a picture we took in Switzerland, in Rapperswil. And yeah, I keep the presentation a bit short and fast because I think we are running out of time. So you can ask questions later on. Thank you very much.
Thank you very much, Daniel. And indeed, we're a bit running out of schedule, but I think we can catch up. I will give the floor now to Raphael to present us heat pumps with natural refrigerants. Rafael, you can share your screen when.
Okay, so did that
Yes.
work? And can you
Yes.
hear me?
Yes.
All right. Warm welcome again to this workshop about applying heat pumps with natural refrigerants. So we do believe that a few futuristic technologies should contain known and safe refrigerants. That's why we chose only natural refrigerants within TriHP, and I would like to present you why. Looking back at the history of refrigerants, we are looking at many changes. So we were using natural refrigerants, which is the fluid that has to circulate within the heat pump. We only used naturals many years ago. So it all started with CO2, with hydrocarbons, ammonia being a very efficient and good refrigerant. Air and ether were also used in very early years, and but there were some issues, as you might know, with safety and toxicity. So the chemical industry came and introduced chemical refrigerants around 1930. Unfortunately, it took us 30 years to realize that they really harmed the ozone layer. As you might know, it took another 30 years to realize that with changing those synthetic refrigerants to another substance, so-called HFCs, they had a really big global warming potential. So we're still using those refrigerants. And again, we are in a transition phase right now. 30 years later, we had to implement restrictions. There was the Kyoto Protocol introduced with amendments a couple of years ago in Paris and Kigali. Now we really need to change and move away from those global warming potential substances. There's another group that is currently discussed or partly implemented, which is another form of HFCs that seem to not be stable in the air. They actually are not, but they are stable. Once they break down, we will see that later on. So there still is a bit of a question mark how it continues, but we are focusing on naturals, and we do believe that this is a real long-term alternative. When choosing a refrigerant for heat pump, we are looking at many options, and unfortunately, there is no refrigerant that covers all applications and only has advantages. As you can see, we have some drawbacks in terms of flammability, toxicity. Some are toxic to humans, some are toxic to the environment, as we heard. So it is a challenge and often a compromise. Talking about quickly opening brackets to these new synthetic refrigerants that are discussed. They are unstable in the air, but they are also very reactive. And at the moment, there is a growing number of negative reports about the effects of these new synthetic substances. It has long been known that they acidify our water through the formation of 3-fluoroacetic acid. TFA as a breakdown product is very stable, so it will remain in our water bodies, and it is a foreign substance. Also, they form toxic decomposition products when they are burnt at high temperatures. They have health hazards at long-term exposure. Also, their production, I really question their production because there's ozone depleting substances that are produced to obtain that chemical. It consumes a lot of energy, CO2 emissions, etc. So we should really be very careful. We do believe that only looking at GWP, global warming, is out of date. So we need a broader view. What I think is very interesting is the National Institute of Standards has looked at 60 million chemicals. They have analyzed, is there anything that is better than the actual synthetic refrigerants that we use? And they came up with the conclusion that there will be no option. If that is the group that we implement, that will be the last group. And if we find out that they cause a lot of problems, the only option that will be left is natural substances. Looking at natural refrigerants, I would like to present 4 groups that we can group them in. There's the hydrocarbons that are widely used, especially in small installations. They can very well be used for heating and cooling. Today, they are used in industrial applications, especially petrochemical applications or pharmaceuticals. They are very suitable also for high temperature applications. That is an increasing demand, and many of us use them at home because very small quantities are uncritical in terms of flammability. Then we have another big group that is carbon dioxide. So using CO2 is a very good way for cooling and heating, especially for domestic hot water production, as we will see later on. It's very suitable for high temperatures. It's also discussed with electric cars because it well behaves with heating and cooling, and this is an increasing demand with decarbonizing our mobility. It's also used in food production, especially drying processes, or again when we need high temperatures. Industry and space heating and cooling is increasing, as mentioned. We have the third group is ammonia, a very old but very, very efficient refrigerant. It's mainly used in bigger industrial applications. It's very suitable for low and high temperatures. The fourth group is collecting everything that remains. You could use air, which is used for air conditioning or very low temperatures. We see an increase in using water as a refrigerant for air conditioning and medium capacities. Due to time, I will skip this slide and jump into the first group that I would like to present applications of. It's using carbon dioxide. So there's a lot of products out there already that you can buy off shelf containing CO2 as a refrigerant. By the way, it's the only refrigerant that is non-toxic for humans and the environment and non-flammable. What we see in the market is an increase in demand for domestic hot water. So if we look at multifamily buildings, the demand for space heating is actually decreasing with better insulation, smarter controls of the building, but the water consumption, hot water consumption remains. So we are shifting our demand to higher temperatures, which is very suitable for CO2. This is why we chose to build one part of our prototypes with CO2. You can see it on the left side. That's how it looks like. By the way, in the very back, I can see if I can point to it here. Those are the 3 gas coolers that you can see that Dani Carbonell mentioned being developed. So they are very small, very compact units. This heat pump that we built within the project has a variable speed compressor. It contains this gas cooler mentioned, and it's efficient because we chose injector technology to be implemented, and we run a flooded evaporation, which makes the unit very efficient. Donnie mentioned applications. I can jump to the next slide, I think. Right, we saw that slide as well. I'm sorry. The 3-part gas cooler as one innovative element of the CO2 heat pump was tested at the university in Trondheim, Norway. and it showed very promising performance. They did measure very low pressure drops. They did measure very high performance. They did achieve the temperatures that we wanted, up to 70 degrees of supply temperature. And we are looking at capacities of 10 kilowatts for the heat pump, and also, of course, for the combination of those 3 gas coolers here. Now, switching to the other group of refrigerants that we wanted to implement with another set of prototypes in the project is hydrocarbons. So we are using propane for another ice slurry heat pump. Those products are also available on the market with containing propane. Mostly they are installed outside. There are even some products that can be installed inside. It's a little bit of a challenge. I will show you later on, but they are available. And I put down one example of an installation with propane. If you have a charge of 150 grams or less, there's basically nothing to care about. You can install that inside or outside, wherever you want. This is our freezers and fridges that we have at home. No restrictions. If we are going up to, I would say, 10 kilowatts or 20 kilowatts with up to 1 kilogram of charge, we have some limitations, but they're very easily manageable. If we are looking at charges up to 5 kilowatts, which corresponds to, I would say, 50 or more kilowatts of heating capacity, then we have some restrictions, but there's pretty easy solutions like a ventilated enclosure, which we implemented in our prototype. This is an example of how an installation can look like. You can see the ventilation duct in the back, a very small pipe, just an additional pipe that is required to ventilate those enclosures in case of a leak of propane. This is how the propane ice prototype looked like that we built within the project. It has also got the variable speed compressor. We can produce domestic hot water at the same time as producing space heating with a small additional heat exchanger that was implemented. As mentioned, it does have a ventilated enclosure to cover the safety, and we're looking at a charge of less than a kilo with this installation that was built and tested 1 year ago. Meanwhile, we are testing the second prototype. Those are some first results, and as you can see, we are running at COPs as expected, comparable with synthetic refrigerants or even a little bit higher. What you can see here is the dependence on variable speeds, again, as expected. Another reason to choose natural refrigerants in heat pumps is the application range of the units. I have put down an example here of some application range of compressors. You can see a brownish application range for a standard R410A, which is a synthetic refrigerant application, which is the inner circle, quite limiting. If we add a special compressor with a synthetic refrigerant that has a vapor injection, which is a modification, it makes the installation more complicated, sophisticated, then we can slightly enlarge the envelope. If you look at the largest envelopes, which are the brown and red lines, that is propane. The first one is the compressor that we use in the second unit. The red line is the compressor that we used in the first prototype. That is a huge advantage with propane. You get high temperatures, wide application envelope. All right, I think that is the last slide. And with this, I can hand over to Xavier for his presentation. Thank you.
Thank you very much, Raphael. We'll give now the floor to Xavier from Tecnalia. to present the experimental results of the dual source heat pump.
Okay. So thank you, Spiridon. 1 moment. Could you hear me and see my screen?
We can hear you. We cannot see your screen yet.
Not yet?
Not coming yet.
Okay. Maybe now.
Yes, yes.
Okay.
Now it's again full screen. Thank you.
Okay, so sorry for the delay.
No worries.
So, of course, I'm going to present the experimental results of the first experimental campaign of the dual source heat exchanger and, of course, the heat pump. The concept of the dual source heat pump, I think that Danny has explained it up, but it's a reversible heat pump that in this case is working with propane as refrigerant. It's reversible, so it's heating and cooling, producing heating and cooling. And it has a quite innovative heat exchanger that this is the dual source heat exchanger that could act as condenser and evaporator. And it's able to exchange heat, of course, with water coming from geothermal boreholes or from any sink or source. I mean, solar or whatever if it's necessary, or directly with air, or it's possible to work with both simultaneously. So it's an excellent solution for situations in which heating and cooling demand are increased, and there are limitations for the expansion of the boreholes or whatever. We can retrofit that with that dual source heat pump, and of course are really beneficial for local cooling and heating networks when integrated as both source or sink, in order to compensate the unexpected demands and variations in the temperature of the network. So as I mentioned, this is the presentation of the results of the first experimental campaign. If you can see, more or less, we have a first prototype that is more a test rig than a compact unit for testing that dual source heat exchanger. So as mentioned, it could work in cooling and heating mode. Here you have the PNID or the, but yeah, it's a reversible heat pump. Nothing special, but it's a special. The special component, as I mentioned, is that dual source heat exchanger. So we are going to present some results. Here are some results taking into account the supply temperature to the dual source heat exchanger in air mode, cooling mode in this case, going air to the dual source heat exchanger at different temperatures, 27, 35, or 46, and of course going to the space conditioning heat exchanger, in this case producing cold water. This is the entrance temperatures to the evaporator, in this case, that is a plate heat exchanger acting as an evaporator. So we can see as well the COPs in heating mode. Afterwards, we are going to comment because are lower than expected, of course, for different temperatures, producing hot water at different temperatures, and having the air, the ambient air, going to the dual source heat exchanger at 7 degrees in this case. So here we can see a comparison in between the predictive models that we developed in the past in order to see the EER or the COP in cooling. It's a comparison in between the model and the experimental results. As could be seen in that case, on cooling mode in air, it works quite fine and quite close to the expected values. On the other hand, as I mentioned, we have in heating mode, we have a deviation in between the expected results and the achieved ones. Of course, they have a reason, and afterwards maybe we are going to emphasize it. But at the end, it's related to the pressure drop that we have in the distributor of the dual source heat exchanger. High pressure drops are produced, and because of that, we are achieving values that are less than expected. Of course, we have introduced those pressure drop values in the model that we use for the simulation and the dimensioning of the dual source heat exchanger. That is our specific goal in that experimental campaign. And of course, in the cooling mode, it's clear that we have a low deviation, and as well in heating mode, but of course introducing to the model the experimental pressure drop that we have achieved. So here you have the capacities, the experimental capacity against the model predicted one, as mentioned in heating mode, introducing the pressure drop. As can be seen, the deviations are more than acceptable, and afterwards we use that models in order to develop the second prototype that you are going to see after some slides. So as mentioned, we can work with air or with water coming from geothermal boreholes. Here you have the comparison in cooling mode. In that case, we have lower COPs as well than expected. But in that case, afterwards we are going to see that is more related to the higher consumption, electricity consumption of the compressor. On the other hand, as mentioned in heating mode, therefore acting the dual source heat exchanger as evaporator, therefore going the refrigerant through the distributor that is causing the high pressure drop that is affecting us, the COP. You can see at different temperatures going to the dual source heat exchanger, the water from the boreholes, and producing different temperature hot water. So as mentioned, in that case, in cooling mode as well, we have a little bit lower COPs than expected, but are more related with the consumption of the compressor that is higher than expected as well. On the other hand, in heating mode, as I mentioned, we have lower values, but related to that pressure drop that we are going to explain afterwards. So, focusing on the dual source heat exchanger, we have validated as well the model that we use for the dimensioning. As I mentioned, in heating mode, we should introduce the pressure drop in those models. So using ground as sink evaporator in the right side of the image, introducing those pressure drop values, the experimental results are with an acceptable deviation in comparison with the model that we use for dimensioning. So taking into account that, we have some values achieved, more or less the unit is designed for 10 kilowatts. So we are achieving in design conditions that values, but of course we have COP reduction mainly in heating mode, because of, as mentioned, the dual source heat exchanger acts as evaporator, and the distributor of that evaporator is affecting us. So for the following prototype, we have modified that component, the number of channels that we have as well. So we are expecting a reduction of that pressure drop that is going to help us to achieve the expected COP values. So it's something in order to see from the first prototype, as I mentioned, it was a test rig in order to test the dual source heat exchanger. Of course, we have a really big volume, internal volume for the dual source heat exchanger. As can be seen, a big reduction was produced for that second prototype. Of course, in the dual source heat exchanger, total heat exchange surface, and as well with the charge, as Rafael mentioned. Of course, we are in that prototype with less than 2 kilograms for air, water, heat pump that is going to be outside. In that case, it's dual, but is going to place it outside. This reduction is interesting. And here you can see the first test bench in the left side, and the second prototype that is really more compact, and the reduction in weight as well is important, mainly in the charge of propane. So this is the end of my presentation. If you have any question, of course, we can answer them afterwards. Thank you.
Thank you very much, Xavier. And I would like to remind to the audience that in case they have any questions after this presentation, there will be a discussion session where they can ask the floor and directly make the questions to the speakers, or they can use the chat function on the bottom right of your screen to write your question in the chat. I will now pass the floor to Thomas Friedrich to introduce us to another dimension, not the technical one, but on the social one, regarding the social acceptance of these systems. Thank you, Thomas.
Thank you, Spiridon. Can you hear me?
Yes, and we can see your screen.
Okay. Yeah, as you said, I follow up the presentations before with the technical background of GHP systems, and I would like to briefly discuss the social acceptance of those systems with you. And wait, sorry. How can I go on with the slides? Like that. Yeah, I would like to discuss the social acceptance of such systems by presenting you our key findings from stakeholder interviews and outcomes that we conducted in national stakeholder workshops in Germany, in Switzerland, in Spain, and in Norway. As part of the Institute for Social Ecological Research in Frankfurt, Germany, we contribute to this project from, well, not from a technical, but from a social scientific perspective. I will very briefly introduce the Institute, because I think we are back on time again. Thank you for the presentators before. As part of the GHP consortium, our institute contributes, well, we do a lot of projects, very and transdisciplinary projects on a variety of topics, but the overarching concern is sustainability, and from all those topics, energy is one of them. And my colleague Emmanuel and I don't have a technical background. We are no engineers, we are social scientists, and being this, we eventually found our way into the GHP consortium, investigating the social acceptance of 3HP systems, and the starting point for considering this system, this social acceptance, is that in the light of European Union and countries' climate targets, it has become clear that the decarbonization of the residential sector cannot or hardly be achieved without heat pumps. So let's install more heat pumps seems to be a very easy answer here, but of course it's much more complicated, since the market coverage of heat pumps varies greatly from country to country, and this is to a variety of framework conditions, like the different climates, different geography, the economy is different, political systems, legal systems, and also the cultural contexts are different, and all of them kind of affect market coverage of heat pumps and thus heat pump systems. So what we have tried to do is to better understand the potential non-technical impacts of 3HP systems by identification of the interests and needs of key stakeholder groups that are in one way or the other important for market penetration, market coverage, and also by exploring the market safety and regulatory barriers that exist, by determining benefits and incentives to overcome those barriers, and by identifying geographical, legal, and cultural differences. Therefore, we did expert interviews with different stakeholder group representatives in Germany, Switzerland, Spain, and Norway. And building on these interviews, building on the results of those interviews, we did national workshops in also those 4 countries. Why these countries? Of course, because our project partners from the 3HP project are there. They are there with their expertise, with their experiences, with their professional networks, but also because those countries have very different framework conditions, different situations, contexts. The climate conditions are obviously different, but not only between Spain and Norway, but also within countries, as the example of Spain shows, for example. The market coverage of heat pumps is very different, and also an important factor is that the rental and ownership structure of the building sector varies greatly. So in both the interviews and the workshops, we included different stakeholder groups that we identified as being very important for market penetration, market rollout. Such stakeholder groups were building owners, investors, architects, heat pump manufacturers, engineers, HVAC planners, technical consultants, representatives from associations, heating installers, etc. And in terms of content, we focused on renewable heating and cooling systems based on electric heat pump systems such as 3HP, including natural refrigerants. So I would like to just briefly summarize some key findings for you, starting with the interviews. So we had different stakeholders, different stakeholder groups, and of course they have different perspectives on such systems. They vary greatly from stakeholder to stakeholder, but there was some crucial topics that we could identify that are important in one way or the other for across all the stakeholder groups. And those topics were economic efficiency. So 3HP systems have to be economic efficient. They have to be simple in designing and implementing, but also in maintaining. They have to be practical, feasible. So they should work in real life contexts, as it were. They need a lot of competence and skill. So there are different traits involved, different expertises that you need. which leads to the fact that cooperation is needed between those trades, which makes it complex, and why this is the reason why simplicity is important. So you see those topics are interrelated somehow, and of course you need public support, a good funding landscape for those systems to be implemented and roll out. So context and scale do matter a lot. This is something that we could conclude from our interviews. So it's the national context, but also within the country, there is great differences regionally and also locally that has to be considered. So there is no one-fits-all solution. However, there are some common features that were mentioned in most or all countries, such as that heat pump systems call for higher skills on the part of planners and installers, especially in existing buildings, that heat pump systems challenge existing business models in the heating sector, meaning the fossil business model, which is still very successful and hard to compete by renewable heating systems. And heat pump systems need a better standardization. So this was mentioned frequently in the interviews. So what we did then is to take the interview results and conduct national stakeholder workshops. Stakeholders here, again, were investors, architects, heat pump manufacturers, HVAC planners, representatives from heat pump and heating installer associations, etc. And in group discussions, we gave them the opportunity to vote to select barriers that they consider to be the most important one in their respective country. And due to this approach, we identified important transnational challenges that were frequently discussed in the workshops. And here you can see 4 very important transnational challenges, which is investment in upfront costs, the split incentive dilemma, the shortage of skilled workers, and the high planning and coordination effort of 3rd-generation heat pump systems. In the second part of the workshop, we asked the participants who are the key stakeholders to drive solutions. And the most frequently mentioned stakeholders were building owners, HVAC planners and installers. And finally, we asked the participants to develop recommendations or possible solutions to overcome those challenges that they discussed and to improve the market uptake of 3HP systems. And their suggestions included, among others, that economic efficiency should be considered over the entire life cycle, that there should be more support for new business models, such as energy contracting, or new finance schemes should be developed, and those systems should be simple and easy to use. Planning tools should be provided. Last but not least, it was frequently mentioned that all those complex solutions and challenges, that they are kind of interdependent from each other, that they are related to each other, which is the reason why they should be tackled in a holistic manner, in a holistic perspective. So, well, you should not only focus on a challenge or one solution, you should also think about those other aspects that are interrelated. So in order to be able to develop successful solutions, it is therefore advisable to consider technical, but also economic and social factors together. So if you are interested in more details and more results and more details about our methodology, you can have a look in our public available full reports on the interviews here on the left side, or the stakeholder workshops on our Zenodo community web page. And yeah, that's the end of my presentation. Thank you very much for your attention, and back to you, Spiridon.
Thank you very much, Thomas, for this presentation. It is actually shed some lights on a very different side from the technical part, which is also very important for having these systems more accepted by market. I would just like to remind to the audience that I have sent in the chat. You can find a link to these reports that Thomas just shared with us, and please feel free to raise your hand and ask the floor in case you have any questions. In the meantime, I have a question for Danny. I think you can see my screen. So it's about since these these different types of heat pumps are still at the experimental phase. Do you think that the technological maturity and demonstration of THP systems in actual environments would enable a wider market uptake of renewable heating and cooling systems?
Yeah, so the project, we say we will reach TRL 5, which means we will test this in the lab in a relevant environment. From this, we would still need a follow-up project where we would demonstrate this in the field, a P&D project. We cannot, we always need to test it on real conditions, so we need another step. But in terms of the wider acceptance or market penetration, I think they have a very good potential because they were developed with the aim to reduce costs. So it's not a system that was developed to improve efficiency or to have some very fancy stuff on it. It was a system that was developed to reduce costs by 10% on the global installation of the system, which is quite significant. So the challenge was to manage the technological problems to get there, and we are getting there. So I think the cost factor will be achieved because we are solving the technological problems of it. And you know that cost is the main driver of wider market penetration. So I'm quite optimistic.
Mm-hmm. Thank you very much for your answer. And by the way, do you think which system do you think that would make a better fit for multifamily buildings in Serbia? This is I think counts like South Europe climate, you know.
Counts of South Europe. I mean,
or continental.
Yeah. So I mean, it depends on the cooling needs. I mean, if cooling is significant, it depends on the type of building. Then I would say they will go with a dual source because our auxiliary system is good for heating, but not for cooling. Cooling is just an add-on. If you have a significant cooling demand, then I would recommend to go to the dual source concept.
Thanks a lot. Maybe I can go to next question. Second. To Rafael about the natural refrigerants. And you mentioned flammability, and you showed us all the timeline or phasing out some harmful refrigerants. And by the way, the person who wrote on the chat was from UN, from the coordinator of the protocol. Do you think that the flammability of natural refrigerants would be an additional barrier for building managers for obtaining the necessary safety permits? We have heard this several times, and so some people say, okay, why do I need some extra permits for CO2 or propane while I have natural gas with less safety measures? I mean, could we have your opinion?
I do think it's a very good and important question. It normally is the first question raised. It's funny, I came across a very old safety data sheet of propane. It's probably 100 years old, and it said on it, safe refrigerant. So many decades ago, they considered it to be safe because it wasn't toxic, but it was flammable. So I do believe that flammability can be handled. Risk is always a question of what's the consequence and what's the probability, and both can be measured or assessed, and they need to. That's daily business of engineers and developing a new installation and machine. You have to put a value to a risk, and because life is dangerous. And I think we all have to work hard to be very cautious with assessing those risks, but also find solutions to keep it safe. So there's a lot going on. There's standards are created, standards are changed. So we have seen a move from, for example, with small light commercial applications, we have moved from 150 grams to 500 grams of a low limit with, you know, appliances in household installations, which is a huge move, and it was possible. So we are actually I know that this limit is discussed currently for heat pumps as well. So we will see change in the future, making things easier. But also, I do believe that people will get used to it, realizing, okay, there is a risk, but we can handle it. And I hope that in 5 or 10 years, people will not be afraid of propane, but have the necessary cautiousness, like we all have with our barbecues on our balcony. We have 5 or 10 kilos in our barbecues and nobody cares. But it is a risk. And so there's good hope and a lot of transition going on with propane.
Exactly, and as you mentioned, and I know, for example, I come from Greece, and my grandmother in the village had the propane bottle for the container for cooking, because there's no natural gas network at that point. So, and there were not any safety concerns, and I guess might be a similar situation in Serbia or another place in Europe. Then I have a question for Xavier about if you could elaborate a bit more about all these really nice and complex tests that you did in the lab. And actually, the question would be, standards have you used to test experimental heat pump? For example, the eco design will require to test these systems according to EN 14511 and or EN 14825. Do you think that this is possible, or maybe you can tell us a bit more about more the standardization part of the test?
Yeah, of course. Related to that issue, in our laboratory, the test that we have performed and the one that we are going to start to perform to the second prototype are in agreement with the EN 14511. Of course, nowadays we haven't already tested with the 14,825, but could be in the future. But in that moment, all the results that we have achieved, we have developed in agreement with the EN 14,511. Yes, and it's a standard in order to test heat pumps, chillers, and so yeah, all the results are in agreement with that standard. The periods in stability periods for an stable measurement in order to take to obtain an average value and whatever are fulfilling the mentioned standard. Yeah, of course, in agreement with the eco-design directive. So yeah, more or less, this is yeah, what I can tell you about that.
Thank you very much. And I remember from your presentation that you showed us actually the facilities in the lab, in the laboratory where you test the heat pumps. And are they placed, what's the surrounding temperature of in the lab? I mean, are they placed in a specific chamber with specific, let's say, climate conditions and outside temperature, or is
yeah, our climatic chamber is able to maintain the temperature and humidity, of course, reproducing the external or the ambient temperature. I mean, of course, when we have been testing the unit inside the climatic chamber, of course, if we are testing with air source or sink, of course, we have we have reproduced the ambient temperatures or different ambient temperatures, and our climatic chamber as well is able to reproduce both. I mean the inside or the inside conditions and outside as well. So yeah, it could test and reproduce both ambient if it's necessary. And linked to that, of course, if someone wants to know it, I don't remember the standard just now, but of course, all of our laboratory is prepared to work with flammable refrigerant, with propane, and of course, they should be detectors and extraction, as previously mentioned by Rafael. We have of course, all the laboratory prepared in order to work with propane. Of course, all the detectors and extraction systems are already available in our lab.
Thank you very much. And maybe I can go to the next question. I don't see any from the audience. They're a bit shy, I guess. I would like to ask Thomas Friedrich. Do you think that communicating the life cycle cost to building managers coupled with environmental and comfort benefits would enhance the acceptance of 3HP systems? We saw that mainly, I mean, the occupants from one side, but also managers care a lot about the upfront costs, but we see also that they are more and more aware about the environmental impact, and this is what we saw actually from the stakeholder workshops in Norway. Do you think that showing that splitting these costs across the lifetime of a heat pump would somehow improve the acceptance of the system?
That's a very good question, Spiridon. Thank you. Well, I'm not economist. I am not good in calculating, but compared or knowing what people told in the interviews, I think it will be important for those that do have environmental higher environmental awareness about the impacts of their heating system. So communicating the life cycle costs would be good thing if it's possible to have a better more fair comparison between fossil heating systems and heat pump systems, since you kind of internalize environmental costs better in the life cycle cost assessment. So that would be well, a good thing, I think. You also asked about thermal comfort and comfort benefits. That's also important, I think. So the co-benefits of those systems, I mean, in general, I think it's good to communicate them. So it's always depending on the target groups, of course. So thermal comfort may not be that important for some building managers if they look on the costs, but it may be important for single home owners, for instance, much more. So tailoring the communication strategies better to target groups is important here. Yeah, and in general, the awareness raising for non-monetary benefits and co-benefits, I think it's very important. Another one is, by the way, is also the self-sufficiency, energy self-sufficiency of those systems. So, because this came also up in many interviews that being energy independent is also a very important thing. People may decide to buy a system or implement such a system.
Mm-hmm. Sorry for this. Thank you very much, Thomas. And please, the other speakers, if they have something to add or compliment, please feel free to unmute yourself and take the floor. I would like to make another question to Danny. And about the supercooling method. So the question is utilizing the supercooling method for heating instead of cooling might be a niche application in the market. How do you see the application of this technology in other fields?
Well, I mean, iSlurry was developed, the concept for cooling applications. It can be refrigeration, for commercial, for industrial, for residential, but this can go to district cooling. Now we are realizing the potential in low temperature district heating grids in Switzerland with this kind of used as a seasonal storage. So the application of iSlurry in itself is huge. We just kind of developed this from an innovation application for the heating, which I always call it niche worldwide, so to say. I mean, in Switzerland, this is becoming very well known, and there are a lot of systems. But of course, this kind of a development. It's for a limited climate region where you have heating needs. Almost no cooling, but you still have sun. I mean, if you bring this to Norway, there is nothing to do there because it's a solar-driven system. Yeah. But for refrigeration itself, it can be used for many applications, and we see a lot of potential there. And even there are developments of thermoelectrical energy storages that they use ice storage on a CO2 times critical cycle, and we are involved in projects with this concept. So the applications is huge on refrigeration side.
Thank you very much. Yes, it's very good information, and not many people are very familiar with these innovations. I would like to, we still have 3 minutes, and I would like to ask both Thomas and Raphael. It's about natural refrigerants, and we saw that it was in Norway or in one of the stakeholder workshops. They considered the use of natural refrigerants as very important aspect of for choosing such technologies. And do you think, Thomas, that can you tell us a bit more on because this is not. I mean, people mainly choose are attracted by the low cost or the design or of these technologies. But we see a shift on the priorities on from consumer sides. On they start caring more about environmental aspects, and this is very promising. I don't know if you want to add something on it, but I find it kind of fascinating and promising message from the market. And please, Rafael and Thomas, if you want to add something.
That I find very interesting indeed is probably the slide that I skipped. I think it's also linked to the long-term thinking that you mentioned, Thomas. For end users, it's so important to think about life cycle cost and also a bit the risk with applying other refrigerants than natural refrigerants. So I do believe that for end users, it's starting to gain importance. Think about what's the consequence of my choice today. So with natural refrigerants, there's so many risks that you can exclude. There's, I mean, when you mention Norway, Scandinavia in general, they have huge taxes on HFCs. There's no risk of being limited with sourcing those substances because they are widely available. No taxes, no other restrictions. We do have the risk that they discover other environmental problems, and then nobody knows what happens to your installations if you have to change it short term. So that really are costs that you should consider.
Thank you very much. I don't know if any other panelist or speaker who wants to add something on it.
Well, since you also asked me just maybe a few final words on that question, I think it's very important to raise the facts that of the global warming potential of refrigerants and the advantage of natural refrigerants, because if we think about how European Union and future developments should bring much more heat pumps into the system, and on the other hand we see that environmental awareness of people and of the general public is raising, so they do care a lot about this. I mean, it's now the time to do it in the right way, right? So well, raising that fact is, I think, very important, that natural refrigerants are much better in this regard than alternatives.
It's going to be probably two ways, a kind of pull and push phenomenon. From one side, the market asking for more environmental friendly technologies. From the other side, imposed by EU policies like gas regulation. It was a very interesting discussion that we had today, and we have reached the end of the available time we had. I hope, I think we received one last question, but I'm afraid we don't have the time to address it. It's for Danny.
I'm trying to read it. So that's well, the way we solve this is we apply it in a different way. So we are not using now an ice storage to shift cooling loads in order to compensate the difference in electricity prices. It was cost efficient before. Maybe it's not now, but it will come, because the electric grid is suffering from a lot of renewables playing into role, and the grid stability is and will be a major thing. So energy storage and anything that can shift loads will become more important. So we are just now applying this into a different field, but this use of ice storage as a heat battery will come, I'm quite sure, in near future.
Thank you very much, Danny. Tamara also thanks you. I would like to thank you all for today's contribution and all these interesting information to show what could be the future of renewable heating and cooling. As I mentioned before, I will share the presentations with all attendees. And I would like to thank again all the speakers that were here today. And have a nice weekend. And hope you enjoyed this workshop. And many greetings to our Serbian colleagues. Have a nice evening.
Thanks for attending.
Bye.